YouTube and start the session link here. And just log into a different device to make sure that this is actually showing up. Okay. Oh, we're seeing the participants are trickling in. Excellent. So we're going to have some people who are going to join directly here and some who I think are going to watch we've got so far 5 people who are watching directly on YouTube as well. So welcome everyone. We'll just take a few minutes to let people find their seats as they're leaving the gather town. Maybe I'll send another announcement just to point out that the Q&A is about to begin. Okay, and with that, I'll try to stop spamming the communication channel on Gather. So let me check one more thing here. We have okay, so we had an opportunity in FeedLoop for each talk. We have a form where you can go and you can upload a question offline if you want to sit down and compose a question. If you're not going to be able to make the Q&A, we haven't got anyone who's taken that opportunity yet, but we'll see perhaps this evening whether someone else has done that. There's also an option for you to potentially upload a video or an audio clip so we can actually have a sense of someone actually really asking a question. All right, so let me say enough sort of throat clearing. Welcome everyone. It's a huge pleasure. You guys, unfortunately, over the week you have the opportunity of watching me give introductions over and over and over again. So I should stop maybe giving the same introductions, but it really is an enormous pleasure to have Larry Matthies here with me. And the purpose of this is to just try to have some engagement, try to have a little bit of that feeling at the end of a talk where you can raise any questions you'd like to raise, and you can have you can see what our speakers have to say. And as a standard moderator, if we don't get any questions, then it falls to me to ask some questions, and I certainly do have some questions. But are there any people any attendees who would like to raise a hand? If you raise a hand, you're welcome to jump in and ask a question. Okay, so if not, maybe I'll prime the pump a little bit, as I said before. Larry, one thing so first of all, wonderful to have you here. Thank you.
My pleasure.
So one thing that I found really quite remarkable in your talk was to see sort of these orders of magnitude improvements, just to see how far really, you know, and it's quite interesting the way you kind of present it. It has great rhetoric in the sense you talk about all the technologies. You say, okay, there's an FPGA, there's a device that does this, and I'm thinking, okay, is that going to make a big difference? And then you show on the very next slide, wow, what a huge difference that makes. You know, but I have to say, it's not that easy for me to kind of put my mind in a space where we're talking about, you know, those processor speeds that are going back some decades now. So one thing that I found remarkable is that the helicopter, you said that originated from a visit in 2013, and 2013 to actually on Mars, flying into 2021. That's a really short time zone. It's a time interval. I mean, is that usual? Is that an exceptional case? Is that just because helicopters are so cool they couldn't say no to you?
No, it's a very exceptional case. It's because the helicopter was a tech demo, so it wasn't required to meet the same standard of reliability. We didn't have to use, you know, standard space qualified parts. Yeah, so that was the main reason. So now, in comparison, the terrain relative navigation capability, we started working on that in about 2005. So that took twice as long, and well, maybe just about the same amount of money, but it took twice as long.
But that was pretty, I mean, incredible to me to go from 15 meters a day to 200 meters a day. I mean, that's a huge, that's a huge thing. One thing you said in your talk was that you did some simulations and you realized that unless you kind of did your viewing and thinking and planning and driving at the same time, you wouldn't make enough progress. You said simulation showed you wouldn't make enough progress. And I didn't quite know what that meant. What is enough progress? Is there a measure that you need to meet?
There is a definite measure that we need to meet. So for a mission like this, and I have to qualify this because I don't necessarily have the exact numbers in my head. So, take this with a little bit of a grain of salt, but, we want to get the prime mission done in something like 2 Mars years. And we need to collect something like 37 samples, give or take, in that amount of time. And we know that we want to cover a certain, distance from A to B. And we can estimate how much time it's going to do all of the science. So we know how many days we've got for driving. So we can work out what our average drive rate has to be. And then we can simulate the terrain and simulate the drives and say, do we think we're going to make it? And if we have to drive around all the rocks, you've got more total traverse time, and you've got more cases where, if you have a very conservative planning strategy that just grows the obstacles as a function of how far away they are because of a kind of a fixed slip estimate, you might find that all of the conceivable paths get choked off, by the time you've gone, half the distance you really need to go. So, therefore we needed to, be able to drive over rocks and be smarter about, the uncertainty as a function of distance. So, again, that wasn't my work. I'm translating my understanding based on, from the colleagues here, but that's the general idea.
That's one thing which showed up, the notion of managing risk and the risk represent. I actually kind of really liked how you spoke about the risk map and the resolution of the risk map and how you computed those things, and that was used. So actually, we've got a question here. I should stop asking you my questions and then we should open to the audience here. So Stefan Schubert has asked this question. What can we expect from a Mars rover that's developed from today in terms of computational power and sensors? And I guess, the end of your talk, you said, currently, the next plan are probably lunar rovers, right? And then, but you said the point there is that there are going to be lessons that are going to learn that would be learned that would have relevance to later Mars, Mars missions. But I mean, I guess if you said you've been working on this, I mean, even if you go back 10 years, 8 years, I mean, that Snapdragon processor didn't exist, I guess, at that point, right? So presumably there's a catch-up process. What can we come to expect from in terms of computational power and so on?
Well, that's a little speculative, but so the helicopter uses a Snapdragon. We would not have been able to use a processor like that in the rover because they're not space qualified. So we could do that in the helicopter because it was a tech demo. But having demonstrated that, there's been interest for a long time in whether we can use, basically commercial grade processors in space instead of having to use rad hard processors that are always, a factor of 10 or more, maybe 100 slower because they're much older technology. So there is potential now, especially on the surface of Mars, because the radiation environment is not that benign, to use things like, commercial processors. There's a couple of possibilities out there, but if you, especially if you use redundant configurations, like we call it triple modular redundancy, where you vote the results. If you get a random bit flip due to a passing cosmic ray in one of them, you can detect that by voting 3 processors and then keep going. And we could potentially have compute power on rovers in the future that's comparable to what's in a phone today. And the other possibility is the automotive industry. with smart cars, driverless cars, they need the kind of reliability for human safety there that we need in space because of cost. And so they're working on reliable computing architectures, and we may be able to leverage some of that as well.
Interesting. Yeah. So when you say they do, you would do some sort of redundancy where you do voting. Would it literally be, is the right way to do that sort of at the processor level, or is it sort of you do a computation at the end, you do some checksums, or is it really like we're talking about bit flips?
They're both options. It depends on exactly what the function is. In some cases, you could just run it multiple times and compare. In some cases, maybe the failure mode is such that it's not that crucial. You just run it once, and if it didn't work out, well, you stop and you run again. Yeah. But things that are really mission critical, you probably want that hardware redundancy so you can check in real time.
I see. So it's quite interesting to me, and your talk kind of made this clear, although it wasn't, I think, an explicit takeaway message of the talk. But one of the things that's kind of interesting is you've got the system, and you have got some parts which are tech demos and some parts which are not. And so you have, in the same system, you have components. I mean, I think one of the helicopter is, of course, the tech demo you spoke of, but I think Moxie was another example of a device which was also listed there, which is a tech demo. And so you have some components which are robust and reliable and expected to be, I guess, a platform, and then others which you have some level of expectation that they may misbehave. And that's kind of interesting to see in a single system. How do you guys approach the sort of the design where you have different teams? Some teams who are operating at the tech demo level, and some people who are building components that are not.
Well, of course, you need the whole system designed so that if the tech demos fail, they don't threaten the success of the main mission. So basically that means the interfaces have to protect the rover. If something happened to Moxie, it can't mess up the rover. If something happened to the helicopter, it can't mess up the rover. So there was a lot of attention paid to, so we put the helicopter underneath the rover. We needed to make sure that didn't mess up anything to do with the rover landing. What if we land on a rock that happens to hit the helicopter? Is that going to make it hard for the rover to move? Yeah. We have another Snapdragon actually on the rover that is communicating with the helicopter. And, we needed to make sure that, nothing on the rover side in the electrical, connections or data transfers had any chance of causing trouble with the rover processor. And then just designing the helicopter operations, because the rover really needs to get on with its business. We needed to have the helicopter operations be as, short amount of time as possible and kind of not interfering with the main mission of the rover.
So the thing you said at the end is you said you had this tech demo, you ran the helicopter, it was a success, then you had kind of the green line on your slide, and you had some other operational demos, and then you said you're going to try to push the boundaries a little more, but at some point you're going to need to stop, because what's really happening is that, maybe I'm putting words in your mouth here, but the rover is a little tied to the helicopter now, because if the rover goes off too far, then there's not much for the helicopter to do. And so it sounds like maybe you're going to have to kind of put that on a pause, have the rover go do its science, and then you can come back and maybe at some later point. Is that sort of correct? Is that what's really going on? Because people get excited, presumably, by the demos. I mean, as I said, I've been following this stuff, and no one was more excited than I was to see this helicopter and to see the first footage of the flight. But there may be a point. I mean, I know people at JPL will talk about the science, the engineers, and it's this thing is not a toy. It's got to do science. And so so is there a broader plan? Maybe the rover will come back, or do you just kind of put a pause on the helicopter? How does that work?
Well, the plan right now is that sometime in August, and I don't remember the exact date, but the plan right now is that sometime in August, the helicopter is done, and it will stop operations, and the rover will just keep going without the helicopter. You know, if it should turn out that we show that the helicopter is really, really helpful to the rover mission, maybe that plan will change. You know, I don't want to create any expectations of that because it's way beyond my pay grade. But right now, the plan is that the helicopter will stop operating sometime in August.
Cool. So we have a question here from Pierre. Pierre, thanks for your question. The question is, what are the open algorithmic challenges for navigation? Adding new capabilities or becoming more power efficient or more reliable?
So there's different dimensions of navigation here. So one is the initial landing of the rover. We did that. We didn't have onboard real-time landing hazard detection. So we mapped all of the landing hazards before the rover got there using orbital images. So you can see most of the landing hazards that way, but some of the smaller rocks we can't see. Or if we ever try to go someplace where we don't have as much orbital imagery before we get there, then we need onboard landing hazard detection. And so that may need different sensors. You know, it might need a LiDAR, or we need better ways of processing the onboard descent imagery. So that's for the lander. For the rover, one of the things I mentioned in the slides is terrain classification. We don't have that on board yet. And so that might be an interesting area where we didn't have the compute capability until now to do deep learning. But with either an FPGA or if we can use modern multi-core processors with you know, deep learning enhancements, maybe we can get better, you know, machine learning on board to do terrain classification and other things. We don't have global localization on board. That's something that we're working on. So, you know, being for the rover to be able to essentially do landmark recognition against orbital images, that would be valuable. You know, that's something we're working on. It's coming along. I think we'll have that soon. For the helicopter, it needs all the things I just mentioned. I mentioned in the talk that we didn't have onboard landing hazard detection in Ingenuity. We've been working on that in the lab. We think we're pretty much ready to go with real-time structure for motion to do landing hazard detection. Well, I'll stop there.
Yeah, I hope that's an answer to your question. If not, okay, so we've got another question here. So do you face any limitations with a wheeled robot? Do you think legged robots or drones can mitigate some of these particular limitations? And if yes, what problems do legged systems and drones have in some such missions? I guess the most, go ahead. Yeah, sorry.
Sorry. There are limitations with a wheeled robot. So in terms of the steepness or the roughness of terrain that they can traverse, or the total range that they can travel in a mission. And also there are some scientific measurements, you know, for atmospheric science where you might like actually to go much higher than a rover can take instruments. So maybe you want to measure water vapor as a function of altitude. So obviously only an aircraft can get up to hundreds of meters or a kilometer of altitude. A drone, we expect, can cover a lot more range than a rover, and it can fly over the rough terrain. If there's science to do on steep slopes, the drone could do that. Limitations of drones are in how much payload it can carry. So because the atmosphere is so thin, we can carry more payload on rovers. And if you have to actually interact with the surface, it's harder, not necessarily impossible, but harder to do sampling operations from a drone than a rover. And legged robots, you know, we've thought about legged robots. You know, it's not clear that there's a use case right now where legged robots are a big advantage. You know, we've thought about it for Europa, which is the big moon of, one of the moons, I should say, of Jupiter. That might be incredibly rough. And it might be that the only practical way to traverse on Europa would be a legged vehicle, but the radiation environment there is so severe that your mission duration is so limited that I don't know that mobility is ever going to be practical on Europa. So I think it's still an open question if and where legged mobility might be useful. Maybe if there's ever good science to do in caves, maybe, but that's an open question too.
I'll pause for a second. Okay. Anne's got a question here. How will the sample recovery rover find the samples left by Perseverance?
That's a great question. So we know very well where Perseverance is all the time, because at the end of every drive, we take imagery from the mast and we register that with the orbital imagery. So we know where Perseverance is to within, a meter or two. So basically we can find them by position. And we believe that the sample tubes will not get buried by sand and dust in the intermediate time. So we think they'll be visible on the surface, and that we can get close enough based on known position to just see them in imagery.
And I hope that's a reasonable answer. So actually, I mean, I'm very curious about this sample return mission, because the time scale of just how ambitious, what a bold attempt that's going to be, involving multiple agencies, multiple phases. And you were talking a little earlier when I was asking about the tech demo components versus the other components that you said about defining interfaces. So what is it like to define an interface that's sort of a contract that says 15 years from now on another planet, this is the module that we're going to leave in the sand, and it's not going to get buried. We're pretty sure it's not going to get buried. Okay, and you guys need to fire that thing out into the atmosphere, and then you got to catch it and then bring it back. I mean, how is that? How is that managed? How do you think on such big scales? As someone I'm very much an academic roboticist. So 5 years, the duration of a grad student's PhD, is the longest we managed to think about. So how do you tame that complexity?
Well, that's a very good way to describe it, taming the complexity. I think that's a big part of the challenge, and an important thing to do is to do exactly that as much as you can. It's the nature of the business that we have very long planning horizons. And yeah, it's a big job, so it takes a long time. I don't know exactly how long sample return, the mission concept has been in the making, but I'll bet we've been working on that for more than a decade. In the kind of the planning stages and the detailed negotiations between NASA and ESA. I was not at all involved in those. I don't know anything about that, but I think that was many years. So there's all the engineering aspects that have to be looked at, and there are always multiple ways to do things. So you're doing these trade-off analyses to figure out what's the best way. And then of course there's a political dimension, right? Because you have to get all of these countries to agree to put up the money all those years ahead. And so you end up having to have these very high-level agreements signed saying, we agree we are going to do this. And so, yeah, it's a long process that takes a lot of work by a lot of people at, ranging from, entry-level engineers to, the big bosses who have to do the negotiation between countries.
Yeah, it's a new definition for full stack, right? It's full stack 100 people. Yeah, no, that's
yeah,
amazing to me. Do we have any other questions in the audience? Sorry, I feel like I could just have a conversation with Larry, but I don't want to hog the microphone here. So I do have kind of a question about, so there's the tech demo, and then there's this operational demo, and then you said, at some point in August, the helicopter's done. But if we look at the earlier rovers, they ran longer and longer and longer and longer than anyone ever expected them to. So so what are the next stages? Is there sort of like at some point you're doing the stuff you need to do, then you're doing the more speculative stuff. At some point you're doing the Hail Mary pass idea, right? The long reach, low probability, but for potentially great value if it works out. What's after operational demos, or is what I'm saying is that not a meaningful way of thinking about missions?
Do you mean for Ingenuity, or do you mean other missions in the future?
I mean for Ingenuity, but
well, okay. So this is totally me speculating. Okay, there's no basis in reality. It's just me thinking aloud. All right. Perseverance needs to get up on top of the Delta. If the rover team thinks it's valuable, maybe it would be useful for the helicopter to get up there and scout on top of the Delta before the rover goes there. That strikes me as potentially useful thing. We started this back in 2013. We called it Mars Helicopter Scout, because we thought that a helicopter would be useful for scouting for a rover to find the safest and most efficient place to drive, and to go get high resolution imagery quite a bit ahead of the rover, so that we could figure out what's the best place to go do the science. So whether or not that could still be useful here, I couldn't say, but that was the original vision. And that would be, I think, basically the spirit of, if we really prove that getting that high resolution imagery, hundreds of meters, half a kilometer ahead of the rover, really helps plan the rover mission. And if we can do the operations without getting in the way of the rover, then maybe somebody will decide it's worthwhile.
I see. And let me just make sure I didn't misunderstand something about your talk. When the helicopter was first released, it was the rover's job to find the safe landing spot for the helicopter. So there's sort of this yin and yang thing, where now what you're saying is the roles have reversed, and if what you're saying, as you said, and as you said, it's sort of all speculative, big caveat there, but there now they're looking out for each other, and that actually swaps, which I think is excellent.
Yeah. I don't know what else to say, but yes.
No. Well, I was asking if I understood, so I think I did. So great. Yeah. So Peter has another question here, which is, what is your opinion about private companies and commercial interests on Mars?
Well, I'd love to have that happen. I think the question we have to ask is, what is the economic incentive for private companies on Mars? And I think it's a little hard to imagine, other than the government saying, we're going to pay you to go do this because of whatever reasons the government has, like science. Are there other economic, commercially viable reasons to go to Mars? The interest in sending people, well, but that's really a government-driven interest. I think space tourism to Mars is not going to be affordable. Let's just forget about that. So it's a little hard for me to imagine commercially viable.
So if you think about something like the closest analogy to this question I could think of is something like the Dutch East India Company. Right, so I think which 200 years ago, however long. I mean, it's a question maybe about sort of ownership, and I think that we've moved on. I don't think we're going to say, oh, you get to go there and you get to build a Starbucks, and now the crater becomes the Starbucks crater. I guess, but I think that there was I might have my history wrong there, but there was an explicit understanding between sort of government, the heads of the kings and queens, heads of state at that time, and those commercial interests. So maybe, and I think in our current world that's all a gray, a gray undefined region. The law doesn't have anything to say about that, I think.
Well, I think the economics of resource exploitation. So back in those days, you could imagine that was going to be economically viable. The costs of going to and returning from Mars are so high it's hard for me to imagine that that could ever be viable. So I have to apologize. We scheduled this for half an hour, right? And I'm going to have to go to another meeting. So
we're done. So thank you very much for your time, Larry.
okay, it was a pleasure.
So we have another one in, what is it, 10 hours, something like this.
Yeah.
And so any of the audience members, the form, if you want to submit if you would like to submit a question or a follow-up question, please feel free to do that. Thank you, Larry. I'll catch up with you on the other side.
Yeah, thank you. Bye.
Okay.